Welcome to this session. Today, we'll tackle LeetCode problem number 1030, matrix cells in distance order. This problem challenges us to return all cells in a matrix sorted by their Manhattan distance from a given center. Stay tuned as we break it down step by step and explore efficient ways to solve it. In this problem, you're working with a matrix defined by its dimensions, rows and cols, and a specific cell within the matrix, identified by its coordinates R-center and C-center. Each cell in the matrix is represented by a pair of indices, R, C, where R is the row number and C is the column number, both starting from 0. The goal is to return all the cells in the matrix, sorted by their Manhattan distance from the center cell, R-center, C-center. The Manhattan distance between two cells, R1, C1, and R2, C2, is calculated as the absolute difference of their row indices, R1, R2, plus the absolute difference of their column indices, C1 and C2. When two cells have the same Manhattan distance, they can appear in any order relative to each other. The input specifies the dimensions of the matrix and the center cell, and the output is an ordered list of cell coordinates based on their distances. Now, let's examine the first example. Here, the matrix has one row and two columns, with the center cell located at 0, 0. The task is to calculate the Manhattan distance of each cell from the center and return the cells in order of their distances. The output for this input is 0, 0, 0, 1. This small example provides a simple setup to understand the ordering of cells based on distance. In this example, the matrix is represented as 0, 1, where the center cell, 0, 0, is at distance 0 from itself. The next cell, 0, 1, is at a distance of 1 from the center. Since there are only two cells, the result is straightforward, 0, 0, 0, 1. The cells are ordered first by their Manhattan distances, from smallest to largest. Next, for a matrix with two rows and two columns, the center cell is at 0, 1. The matrix can be visualized as 0, 1, 2, 3. The center cell, 0, 1, has a distance of 0 from itself. The cell, 0, 0, is at a distance of 1, as is the cell, 1, 1. Finally, 1, 0, is at a distance of 2. After sorting the cells by their distances, the result is 0, 1, 0, 0, 1, 1, 1, 0. Notice that cells with the same Manhattan distance, like 0, 0, and 1, 1, can appear in any relative order. In the third example, the matrix has three rows and three columns, and the center cell is at 0, 0. The matrix looks like this: 0, 1, 2, 3, 4, 5, 6, 7, 8. The distances from the center cell, 0, 0, are calculated for each cell. For instance, 0, 0, has a distance of 0, 0, 1, and 1, 0, both have a distance of 1, and so on. The cells are then sorted by their distances, resulting in the output 0, 0, 0, 1, 1, 0, 0, 2, 1, 1, 2, 0, 1, 2, 2, 1, 2, 2. The key here is to correctly calculate and order the cells by their Manhattan distance. There are some important constraints and edge cases to consider. The dimensions of the matrix are limited to 1 to 100 for both rows and columns, and the center cell must always be within the bounds of the matrix. For edge cases, consider a single-cell matrix where the only cell is the center. The result will always be R-center, C-center. For rectangular matrices where rows and columns are unequal, ensure that the distance calculation and ordering are accurate in both directions. Finally, for large matrices, such as those with 100 rows and 100 columns, the solution must remain efficient and respect the problem's constraints. To solve LeetCode problem number 1030, the objective is to sort all cells in a matrix based on their Manhattan distance from a given center, R-center, C-center. The Manhattan distance is calculated as the sum of the absolute differences of the row and column indices. One straightforward method to achieve this is the brute force approach, where we iterate over all cells in the matrix, compute their distances from the center, store these cells along with their distances in a list, and then sort the list. While this method is simple and intuitive, it relies on sorting, which has a time complexity of O, n log n, where n is the total number of cells. This makes it less efficient for larger matrices. Another approach is the optimized BFS, where we directly generate the cells in the correct order of their distances using a breadth-first traversal. By avoiding sorting, BFS reduces the time complexity to O, n. The third method considered is bucket sort, where we group cells based on their distances into buckets and then concatenate these buckets in order. This method also achieves O(n) time complexity but requires additional space for creating and managing the buckets. The BFS approach starts by initializing a queue with the center cell, R center, C center, and marking it as visited. From there, we process cells layer by layer, where each layer corresponds to cells at the same distance from the center. Neighbors of the current cell are added to the queue if they are within bounds and haven't been visited yet. As each cell is processed, it is appended to the result list. This ensures that cells are added in increasing order of their distances. The BFS approach is efficient as it processes each cell exactly once, resulting in a time and space complexity of O(n). However, the main challenge with BFS is that it can be more complex to implement correctly compared to sorting-based methods. The bucket sort approach, on the other hand, leverages the fact that the maximum Manhattan distance in the matrix is bounded by rows plus cols, too. By creating a fixed number of buckets and placing each cell into the bucket corresponding to its distance, we can avoid sorting entirely. After processing all cells, the buckets are concatenated in increasing order of distances. While this method is efficient, it requires extra memory for the buckets, which may be a limitation for very large matrices. The optimized BFS approach was chosen as the final solution for several reasons. First, it is more efficient than the brute force method because it avoids the overhead of sorting. BFS also naturally generates cells in the desired order of increasing distances, eliminating the need for additional post-processing. In terms of memory usage, BFS is more practical than bucket sort since it does not involve creating extra buckets. Additionally, BFS is easier to implement and debug compared to bucket sort because it builds on well-known graph traversal techniques. The key insight behind choosing BFS was realizing that sorting is unnecessary when we can directly generate the cells in the correct order. The problem's structure lends itself perfectly to a layered traversal, which BFS efficiently handles. Another important observation was that the maximum possible distance in the matrix is finite, which inspired the exploration of bucket sort as an alternative. Each approach has its own trade-offs. The brute force method is straightforward to implement but becomes inefficient for large inputs due to its reliance on sorting. Bucket sort is time efficient but requires additional memory to store the buckets, which might be a concern for very large matrices. The BFS approach strikes the best balance between time efficiency and memory usage. It avoids the overhead of sorting, processes each cell exactly once, and does not require additional data structures like buckets. This makes it the most practical solution for this problem. In conclusion, the BFS approach stands out as both efficient and elegant. It leverages the layered structure of the problem to generate cells directly in the correct order, avoiding unnecessary computations and achieving optimal performance. In this problem, we are tasked with sorting all the cells of an MXN matrix based on their Manhattan distance from a given center point. The Manhattan distance between 2 points is calculated as the sum of the absolute differences of their row and column indices. For example, the distance between R1, C1, and R2, C2 is simply R1, R2 plus C1, C2. The challenge lies in ensuring that the cells are returned in ascending order of their distance from the center. If two cells happen to have the same distance, it's acceptable for their relative order to be arbitrary. To solve this, we can use a brute force approach, starting by defining the matrix dimensions and initializing an empty list to store cells along with their computed distances. We'll then traverse the entire matrix to gather this data, which sets the stage for organizing it in the required order. We begin by iterating through all the rows and columns of the matrix using nested loops. For each cell at position R, C, we compute its Manhattan distance to the given center point, R center, C center, using the formula distance equals abs, R center, plus abs, C center. Once the distance is calculated, we store it in a tuple along with the cell's coordinates, i.e., distance, R, C, and add this tuple to our result list. After collecting this data for all cells, the next step is to sort the list. We utilize Python's built-in sorting function to arrange the tuples by their distance values in ascending order. This step is crucial because it ensures the output adheres to the problem's requirement of sorting by distance. Finally, after sorting the list, we extract only the coordinates of the cells, leaving out the distance values, and prepare the final result list to return. There are several key insights that make this approach effective. First, the use of Manhattan distance is computationally efficient, as it only involves absolute differences, avoiding the need for complex mathematical operations. Second, sorting the cells ensures the correctness of the output. Python's built-in sorting algorithm, timsort, operates with a time complexity of O, k log k, where k is the total number of cells in the matrix, which equals m multiplied by n. While the brute force approach may not be the most optimized for large matrices, it is straightforward to implement and debug, making it a practical starting point. The algorithm primarily relies on a list of tuples to store cells and their distances, which facilitates sorting and later extraction of coordinates. After sorting, we construct a final list of just the cell coordinates, which becomes the result. This simplicity makes the brute force approach a viable solution for small to moderately sized matrices. When analyzing this algorithm's complexity, the time required to traverse all cells and compute their distances is O, m*n. Sorting the resulting list of tuples adds a complexity of O, k log k, where k equals the total number of cells, or m*n. Extracting the coordinates from the sorted list takes an additional O, k, making the overall time complexity O, m*n log m*n. For space complexity, the result list requires O, m*n, to store all cells and their distances, and the sorting process also uses O, m*n, space. Thus, the total space complexity is O, m*n. This algorithm also handles various edge cases seamlessly. For example, it works correctly for a matrix with only one cell, non-square matrices, and cases where the center is on the edge or corner. If two cells have the same distance, their relative order in the output is arbitrary, as allowed by the problem. For larger matrices, an alternative optimization using bucket sorting could eliminate the need for sorting, reducing the time complexity to O, m*n. Here's the Python implementation of the brute force algorithm we've just discussed. We start by initializing an empty result list. Next, we use nested loops to traverse the matrix, calculating the Manhattan distance for each cell relative to the center. Each cell's distance and coordinates are stored as a tuple in the result list. After collecting all the data, the result list is sorted based on the distance values using Python's built-in sort function. Finally, we extract only the coordinates from the sorted list to construct the output. This implementation directly follows the steps outlined earlier and is both concise and easy to understand, making it an excellent solution for this problem when dealing with small to moderately sized matrices. This solution defines a function all cells dist order inside a class solution to solve LeetCode problem number 1030. The function takes four parameters: the dimensions of the matrix, m and n, and the coordinates of the center cell, r-center and c-center. The goal is to return all matrix cells sorted by their Manhattan distance from the center. 1. Initialize the list of cells. We first create an empty list cells to store all cell coordinates in the matrix. 2. Generate all cell coordinates. Using nested loops, we iterate through each row, and column, col, in the matrix. All valid cell coordinates, row, col, are appended to the cells list. 3. Sort by Manhattan distance. The sort function is used to reorder the cells list based on their Manhattan distance from the center, r-center, c-center. The sorting key is calculated as abs, cell, 0, r-center, plus abs, cell, 1, c-center, which is the formula for Manhattan distance. 4. Return the sorted list. After sorting, the ordered list of cells is returned. This approach ensures correctness and simplicity by leveraging Python's built-in sorting capabilities. The sorting step is efficient with a time complexity of O, m*n log m*n. This is appropriate given that the input matrix size is bounded by constraints. The solution handles edge cases such as very small matrices, 1 by 1, or large distances gracefully by treating all cells uniformly. Overall, the implementation is concise, efficient, and adheres to the problem's requirements. In this implementation, we start by importing the necessary packages and defining our solution class. The method allCellsDist order takes four parameters: the number of rows m, the number of columns n, and the coordinates of the reference cell, r-center and c-center. Inside the method, we first create a list called cells to store all the coordinates of the matrix. Using nested loops, we iterate through every row and column combination in the matrix and add each coordinate as an integer array to the cells list. Next, we sort this list of cells based on their Manhattan distance from the reference cell. The Manhattan distance is calculated as the absolute difference in rows plus the absolute difference in columns. To achieve this, we use the sort method with a custom comparator. The comparator calculates the distance for two cells and compares them, ensuring that cells closer to the reference point appear earlier in the sorted list. Once the sorting is complete, we create a new 2D array called result and populate it with the sorted coordinates from the cells list. Finally, we return the result array, which contains all the matrix cells sorted by their Manhattan distance from the reference point. This completes the implementation of the method. The approach is simple and leverages Java's built-in utilities like lists and sorting to achieve the desired output efficiently. By iterating through the matrix once to collect the cells and then sorting them based on their distances, we ensure clarity and maintainability in the code. To solve this problem, we start with a small matrix example where m equals 2, n equals 3, and the center is at 0, 1. First, we create an empty list called cells, which will hold all the coordinates of the matrix. Next, we populate this list by iterating over the rows and columns of the matrix. For each cell, we add its coordinates as a tuple, row, call, to the list. After this step, the cells list contains all the matrix coordinates in row major order 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Now, we need to sort these cells based on their Manhattan distance from the center 0, 1. The Manhattan distance is calculated using the formula, the absolute difference between the row indices plus the absolute difference between the column indices. Sorting the cells by this distance rearranges the list so that cells closer to the center appear first. After sorting the cells list by their Manhattan distance from the center, 0, 1, the order becomes 0, 1, 0, 0, 0, 2, 1, 1, 1, 0, 1, 2. This arrangement ensures that the cells are listed in increasing order of their distance from the center. Finally, we return this sorted list as the output. Moving on to a square matrix example, consider a 3x3 matrix with the center at 1, 1. Again, we start by initializing an empty list cells and populate it with all the matrix coordinates. After adding all the cells, the list becomes 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Once we have all the cells, we calculate their Manhattan distances from the center, 1, 1, and sort them accordingly. For the 3x3 matrix with the center at 1, 1, sorting the cells list by Manhattan distance gives us the order 1, 1, 0, 1, 1, 0, 1, 2, 2, 1, 0, 0, 0, 2, 2, 0, 2, 2. The center cell, 1, 1, comes first, as it has a distance of 0. Then we see the cells directly adjacent to the center, followed by those that are farther away. This sorted list represents the desired output, which we return. Now, let's look at a rectangular matrix example. Suppose we have a matrix with dimensions 3x2 and the center is at 2, 0. As before, we begin by initializing an empty list cells and populating it with all the coordinates of the matrix. After adding all the cells, the list becomes 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1. The next step is to calculate the Manhattan distance of each cell from the center, 2, 0. For the 3x2 matrix with the center at 2, 0, sorting the cells list by Manhattan distance results in the order 2, 0, 1, 0, 2, 1, 0, 0, 1, 1, 0, 1. The center cell, 2, 0, is listed first, followed by cells at increasing distances. This sorted arrangement ensures that we have the cells ordered correctly based on their proximity to the center. Finally, we return this sorted list as the output. By following the same approach for any matrix size and center position, we can efficiently generate the required order of cells based on Manhattan distance. To analyze the time complexity of the solution, we begin with the process of matrix cell collection. Here, the algorithm iterates through all rows and columns of the matrix to gather every cell. Since there are m rows and n columns, the total number of cells is m*n. Consequently, this operation requires O(m*n) time, as each cell is processed exactly once during this traversal. Next, the algorithm sorts these cells based on their Manhattan distance. The sorting step relies on the timsort algorithm, which has a time complexity of O, k asterisk log, k, where k is the number of elements being sorted. In this case, k is equal to the total number of cells, or m asterisk n. Additionally, during the sorting process, a lambda function computes the Manhattan distance for each cell comparison. Since calculating the Manhattan distance involves a few basic arithmetic operations, it takes constant time, or O1, for each comparison. Combining these factors, the sorting step contributes a time complexity of O, m asterisk n, asterisk log, m asterisk n, to the overall solution, making it the most computationally expensive step. Once the cells are sorted, the final step is to return the sorted list. Since the list is directly returned without any additional operations, this step is performed in constant time, or O1. When we consider all the steps together, the total time complexity of the solution is dominated by the sorting step, which results in a final time complexity of O, m asterisk n, asterisk log, m asterisk n. Now, looking at the space complexity, the first contributing factor is the storage for the list of matrix cells. This list stores all m asterisk n cells, so it requires O, m asterisk n, space. Additionally, the sorting process using timsort demands auxiliary space for merging. In the worst case, this auxiliary space complexity is proportional to the number of elements being sorted, which is also O, m asterisk n. Therefore, the sorting step adds an additional O, m asterisk n, to the space requirements. When we combine these factors, the total space complexity of the solution is O, m asterisk n, driven by the storage for the list of cells and the auxiliary space used during sorting. This linear growth in space requirement is acceptable given that it scales directly with the size of the input matrix. Comparing this method to a brute force approach, the brute force method would involve calculating the distance for each cell during traversal and inserting these cells into a sorted structure repeatedly. This could result in additional operations for insertion or resorting, leading to a time complexity that is similar or worse than the current approach. By contrast, the current method optimizes the process by collecting all cells first and performing the sorting operation only once. This eliminates redundant computations, making the solution both efficient and practical within the given constraints. Now, let's consider the best, average, and worst-case scenarios for this solution. In the best case, where the matrix is very small, such as a 1x1 matrix, both the traversal and sorting steps are trivial. Here, the time complexity simplifies to O1, as there is minimal computation involved. For larger matrices, the average and worst cases are governed by the sorting step, which has a time complexity of O, m asterisk n, asterisk log, m asterisk n. Since all elements must be sorted irrespective of their initial arrangement, the average and worst cases have the same computational cost. Finally, the mathematical justification lies in understanding that the sorting step, which uses the timsort algorithm, dominates the overall time complexity. With m asterisk n cells to sort, this results in a complexity of O, m asterisk n, asterisk log, m asterisk n. The traversal step, which collects the cells, adds O, m asterisk n, but this is overshadowed by the sorting step. Similarly, the space complexity is dictated by the storage of the cells list, amounting to O, m asterisk n. Together, these insights confirm that the solution is both time and space efficient, given the problem constraints. When solving this problem, there are several common pitfalls to be aware of. First, incorrect sorting logic is a frequent mistake. To ensure correctness, remember that the Manhattan distance is calculated as the absolute difference of rows plus the absolute difference of columns, abs, R center, plus abs, C center. Sorting should prioritize the distance, and in the case of ties, the row and column indices should be used as secondary criteria. Errors here can cause incorrect outputs, especially for edge cases. Another issue is inefficiency in brute force approaches. Calculating the distance for every cell repeatedly during sorting can be computationally expensive. A better solution is to pre-compute distances and use an efficient sorting algorithm to optimize performance. Additionally, incorrect matrix bounds can lead to problems like accessing invalid indices or skipping cells entirely. Always validate that your loops respect the valid dimensions of the matrix. Lastly, hard-coding matrix dimensions instead of using the given m and n parameters can result in a lack of flexibility, especially when the problem constraints change. Always ensure your solution dynamically adapts to the input dimensions. Another common oversight is failing to account for edge cases. For example, single row or single column matrices, or when the center is positioned at a corner, can reveal flaws in sorting or traversal logic. These edge cases must be tested thoroughly to ensure robustness. Now, let's discuss some key patterns and insights relevant to interviews. Sorting by a computed metric, such as Manhattan distance, is a recurring theme in matrix traversal problems. Being fluent in implementing custom sorting logic is a valuable skill. To optimize further, consider using a breadth-first search (BFS) approach to traverse cells in increasing distance order, which eliminates the overhead of sorting entirely. Additionally, it's important to clarify constraints during an interview, such as the matrix size, the center's location, and whether ties require specific handling. Finally, make sure to articulate the trade-offs between sorting-based methods and BFS. For instance, sorting approaches are straightforward but less efficient, while BFS can be faster but requires a different thought process and implementation effort. Clear communication of these trade-offs can impress interviewers. This problem also connects to several related challenges that can help deepen your understanding. For example, LeetCode 296, Best Meeting Point, shares the goal of minimizing Manhattan distances. LeetCode 54, Spiral Matrix, involves navigating a matrix in a specific order, which is another traversal pattern. LeetCode 1086, High 5, emphasizes sorting with custom metrics, and LeetCode 1162, As Far from Land as Possible, demonstrates how BFS applies in a matrix context. Now, let's examine alternative approaches and their trade-offs. The sorting-based approach involves computing distances for all cells and then sorting them. While this method is simple to implement, its time complexity is O, m*n*log, m*n, which may not scale well for large matrices. On the other hand, BFS begins at the center and expands outward, visiting cells in order of increasing distance. This method has a time complexity of O, m*n*, as each cell is processed only once. While BFS is more efficient for larger matrices, it does require additional logic to handle the traversal, making the implementation slightly more complex. Another alternative worth considering is the bucket sort approach, which groups cells by their Manhattan distance into buckets. Once all cells are categorized, you can iterate through the buckets in increasing distance order. This method avoids the computational cost of sorting altogether, resulting in a time complexity of O, m*n. The trade-off here is that the implementation can be slightly more elaborate, as you need to manage the buckets and ensure proper indexing. However, for large matrices, this approach is highly efficient and can outperform both traditional sorting and BFS. Each of these methods has its own strengths and weaknesses, and the best choice often depends on the specific problem constraints and the size of the input matrix. Being able to weigh these trade-offs and adapt your approach accordingly is an excellent skill to demonstrate during interviews or when tackling variations of this problem. That's a wrap. We explored the problem matrix cells in distance order, broke it down, and discussed the key concepts and takeaways. Thanks for tuning in, and don't forget to subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!